Section 1 Introduction. We're here to talk about large language models, or LLMs for short. These models have shown impressive capabilities and versatility. However, training these massive models, particularly transformers, requires a lot of computing power and memory. This is a resource that most researchers, academic institutions, and even companies don't have easy access to. Even running these models, which is less resource-intensive, still requires a lot of engineering effort. So, speeding up these big transformers is a crucial area of research. In the past, researchers have used a method called mixture of experts, MO-based feed-forward multi-layer perceptron, MLP, layers to scale up transformers. However, these studies didn't really look into how efficient MOs are in terms of parameters. MO models were usually compared to dense baselines with the same number of flops, floating point operations per second, but fewer parameters. It was generally believed that MOs couldn't compete with their dense counterparts when it came to parameters. Recently, a new MO model, called Sigma MO, was proposed. This model not only speeds up transformer training by reducing resource requirements, but it also performs as well as, even better than, its dense counterparts with the same number of parameters. This shows that MOs have potential when it comes to scaling up neural networks. Most MO research focuses on speeding up MLPs. However, attention layers also use a lot of computing power and memory in transformers, especially for long context sizes. Existing methods, like linear attention, often fail to significantly speed up the process and usually underperform compared to its quadratic counterpart. MO-based approaches for attention have been proposed, but they only achieve a modest reduction in computing and memory requirements and usually require a lot of engineering tricks for successful training. We're introducing a new MO-based attention mechanism, called SwitchHead. This reduces the number of attention matrices that need to be computed and stored. Our method is based on the Sigma MO and doesn't require any extra tricks for stable training. We've tested our method on various language modeling datasets and 2 model sizes. We found that SwitchHead performs as well as parameter-matched baselines, but with a fraction of the computing and memory budget. We also introduced the SwitchAll model, a fully MO-based transformer model that combines a Sigma MO-based MLP layer with our SwitchHead attention. This model often outperforms dense baselines with the same parameter budgets. We also analyzed the attention maps of our SwitchHead and found that the maximum of attention maps taken over all heads are similar to the dense baselines. This indicates a significant reduction in redundancy without a loss of expressivity. Plus, expert selections are often interpretable. Now, let's talk about the standard multi-head self-attention, MHA, layer. This layer consists of 4 major steps: computing key, K, query, Q, and value, V, projections, computing the attention matrix, using the attention matrix to project the values, and mapping the projected values to the output. Let's denote positive integers as H, T, D underscore model, and D underscore head. Let's denote an input to the MHA layer as X, T as the sequence length, and D underscore model as the size of the hidden representations of the model. The projection matrices for head H are denoted as W underscore K, W underscore V, and W underscore Q. The keys, queries, and values are then calculated as K equals XW underscore K, Q equals XW underscore Q, and V equals XW underscore versus. The attention matrix for the head H, denoted as A, and the output Y are calculated as follows: A equals softmax, QK caret T, SQRT, D underscore model, and Y equals W underscore O, A caret 0 volts caret 0, A caret 1 volt caret 1. A caret HV caret H, where, denotes concatenation in the last dimension, and the softmax function is also over the last dimension. However, an alternative formulation reflects the role of W underscore O better. Let's divide W underscore O along the second dimension into matrices for each head, denoted as W underscore O caret H. In this case, the output can be equivalently written as Y equals sum, W underscore O caret ha caret HV caret H. From this, it can be seen that all computations are local to the heads. Computing the attention matrix A caret H and the readout A caret HV caret H requires compute in order of O, HD underscore head T squared, max, multiplication accumulation operation. During training, it requires the storage of O, HT squared, for the attention matrices and O, HTD underscore head, numbers for storing the sub-results of the projections. Section Summary. Large language models, LLMs, like transformers require significant computing power and memory, making them inaccessible to many researchers and institutions. Mixture of experts, MO-based approaches have been used to scale up transformers, but their parameter efficiency has not been thoroughly studied. In this paper, the authors propose a novel MO-based attention mechanism called SwitchHead, which reduces the number of attention matrices and achieves comparable performance to dense baselines with less compute and memory usage. Section 2.2 From Dense to SwitchHead. In this section, we aim to reduce the resources used while maintaining the key properties of attention and keeping a fully expressive attention matrix. We question whether the large number of heads used in modern language models is necessary. As we'll discuss later, simply reducing the number of heads while keeping the same number of parameters can lead to a drop in performance. We propose several reasons why many heads might be needed. They could provide multiple inputs for the network's operations. They might be specialized for specific operations, or they could offer different initializations for better learning. If not all heads are needed at the same time, we could potentially save resources by switching between them. One way to do this is by creating a gating signal using a linear projection, and then using the heads with the highest activation. This involves choosing a subset of attention heads for each output position. We found that this method works for language modeling on Wikitext 103, but it's hard to speed up the process or save memory with this approach. This is because the attention matrix depends on pairs of inputs in different positions, but the choice is made only based on the output position. In the worst case, all possible projections have to be calculated for the keys and values, which we want to avoid. Instead, we suggest performing the conditional computation on the projections, separately for the source side, K and V, and the destination side, Q and output. This avoids conditional computation that involves the attention matrix itself. To make the projections conditional, we can use a mixture of experts, MOs. In this case, the concept of heads is not well defined anymore. So, we define a head to be a specific, computed attention matrix. For each head, we define a list of E-experts. Then, the projection matrices become specific to each head and expert. We then calculate the source side expert selection and the destination side experts in a similar way. The value projection is computed as a weighted sum of the selected experts. The key and query projections are calculated in a similar way. The output projection also becomes a mixture of experts. As we'll show, it's not necessary to make all projections MOs. We find that keeping a single copy of the projections Q and K and reusing them for all experts is beneficial. We call this method SwitchHead. If this method can reduce the number of heads by having more experts, it provides an easy way to reduce the resource requirements of MHA. Our method is not dependent on the specific implementation of the attention, allowing for easy experimentation and research. A schematic representation is shown in Fig. Unlike standard MO methods, we found that no regularization is necessary to achieve good performance with our method. Section Summary. The section discusses the need for multiple attention heads in language models and proposes a method called SwitchHead to reduce the number of heads while maintaining performance. The SwitchHead method uses a mixture of experts approach, where each head is defined as a computed attention matrix and a list of experts. By performing conditional computation on the projections independently for the source and destination sides, the method achieves resource savings without compromising the model's performance. Section 2.3 Resource Usage of Different Methods. In this section, we're going to talk about how different attention methods use computational and memory resources. We'll measure computational usage by the number of multiply accumulate operations, or MAX, which is a more precise measure than FLOPS, floating point operations per second. We'll present all calculations for a single attention layer for a single sequence, and remember that both memory and computational requirements increase proportionally with the batch size and the number of layers. Let's imagine a sequence of inputs of length t, with a representation size of d_model. Let d_head be the width of the k, q, and v projections used for the attention layer. For transformer XL style attention, let the size of the context be ct, where C1 is the number of past chunks included in the context of the current attention step. We can split the computation into two main parts, calculating the projections, which don't involve the attention map, and calculating the attention map and projecting the sequence of values using it. First, let's look at the standard transformer XL. Here, from the input x in R to the power of t times d underscore model, we calculate the k, q, and v in R to the power of t times d underscore head using projection matrices of shape R to the power of d underscore model times d underscore head. The output after the attention is projected in a similar way. So, the projections take a total of 4t times d underscore model times d underscore head max per head. For backpropagation, we have to store all the intermediate results. This takes t times d underscore head numbers of k, q, and v also. The projected values should be stored. They have the same shape, so the total memory used by projections is 4t times d underscore head numbers per head. Now let's consider the resource usage related to the attention matrix. It involves calculating the product of q times the transpose of k, which takes d underscore head times ct squared max. The projection of the values with the attention matrix A times v is similar. For the memory usage, the attention needs ct squared numbers, but it needs to be stored both before and after the activation function. In addition, calculating the projection of the position encodings is necessary. This depends on the implementation, but in our case, it involves a matrix multiplication, and the total amount of computation is 2 times d underscore head times d underscore model times tc, and it needs 2 times d underscore head times tc numbers of storage. The resource usage of SwitchHead is different. First, the number of heads h is significantly reduced, but d underscore head is typically larger. Also, there are k experts active at the same time. Here, we only consider the case where the value and outputs are experts, but q and k are not. Then, we have two projections that are identical with that of transformer XL, and two Mo-based projections. These use tk times d underscore model times d underscore head max to calculate the projection and another tk times d underscore head to calculate their weighted average. With a smart kernel implementation, memory usage is not affected by k, thus the formula remains the same as before. Additionally, the expert selection logic needs minimal additional resources, which can be ignored. Note that the comparison between the max of the standard and SwitchHead depends on the exact values of the hyperparameters. However, as we'll see later, in our typical configurations, SwitchHead provides good predictive performance with significantly lower H compared to the standard transformer, resulting in reduced resource usage in the end. Section Summary. In this section, the authors discuss the resource usage of different attention variants. They define compute in terms of multiply accumulate operations, max, and present calculations for a single attention layer and sequence. The resource requirements for the standard transformer XL and SwitchHead are presented, showing that SwitchHead can provide good predictive performance with lower resource usage compared to the standard transformer. Section 3 Experiments. In this section, we'll discuss the experiments we conducted to test our language models. We chose to use a parameter match setting for these experiments, as it better reflects the expressivity of language models compared to the flops match setting often used to evaluate mixtures of experts, MOs. In a parameter match setting, we can't simply add more experts to compensate for a weaker method, as is often done with MOs. Instead, we used a systematic procedure to match the number of parameters of different models. First, we measured the parameter count of the dense transformer, which served as our target. Then, for each method, we set the total number of experts to the same as the original number of heads. We increased the head projection size to the maximum that kept the parameter count below our target. However, because our CUDA kernel only supports head projection sizes that are multiples of 4, this often remained below the parameter count of the baseline. To compensate, we slightly increased the feed-forward network dimension until we achieved a match that differed from our target by no more than 100,000 parameters but never exceeded it. We don't claim that this parameter matching method is optimal, but it's consistent and doesn't require tuning, which would be prohibitively expensive and would have to be done for each model separately. We used sub-word units obtained with a sentence piece tokenizer with a vocabulary size of 8,000 tokens for all datasets except the character level NWIC 8. All models, including ours, are Transformer XL, with the context size being twice the size of the active, current chunk. All models are trained for 100,000 batches. We also investigated which projections require an MO. Each linear projection can potentially be replaced by an MO. However, having experts where they are not necessary can have a negative effect. They can reduce the number of parameters available for the more useful parts of the model. We found that the output projection is necessary to match the performance of the baseline. Having key and query experts seems to be unnecessary. The best performing model is the one with experts for both value and output projections. We compared our method with the mixture of attention heads, MOA, which uses a selection mechanism to choose active attention heads from a set of experts. However, they have a single set of key and value projections shared between experts. In the original paper, the authors use a high number of selected heads, which seems necessary to achieve good performance. However, this means the resource reductions are moderate. Moreover, MOA uses 3 different regularizers, which have to be tuned independently. We found that with non-competitive selection, no regularization is required, and the predictive performance usually is superior to the original formulation. However, it still underperforms our method given a similar computation and memory budget. We tested our methods on a diverse set of language modeling datasets at 2 different scales, a 47 million and a 262 million parameters. Our models always closely match the performance of the full, many-head baseline with the fraction of memory and compute requirements. Importantly, our method also achieves a wall clock speedup, enough to accelerate the entire training pipeline by a factor of around 1.5. This confirms the competitiveness of our method. Section Summary. In this section, the authors describe their experiments in a parameter-matched setting to evaluate the performance of language models. They use a systematic procedure to match the number of parameters of different models and compare them to a baseline. They find that the output projection is necessary for matching the performance of the baseline, while key and query experts are unnecessary. They also compare their method to the mixture of attention heads, MOA, and show that their method outperforms MOA in terms of predictive performance given a similar computation and memory budget. Additionally, they test their method on different language modeling datasets and show that it closely matches the performance of the full, many-head baseline while achieving a wall clock speedup. Section 3.3.1 Switch All. We aim to make transformers more resource efficient by reducing the resource demands of both the MLP and attention layers. A method called MO has been proposed to speed up the MLP layers. However, it's not clear if this method can be effectively combined with our SwitchHead technique, or if it might have a negative impact when used in a switch-all setup, where every layer is MO-based. To test this, we used the architecture proposed by the original authors, without changing any parameters, and replaced the attention layer with SwitchHead. The parameters for the attention were taken directly from previous experiments. The results showed that the fully MO model often performed better than the dense baselines for each dataset and model size we considered, except for the 259M parameter model on the C4 dataset. So far, all of our experiments have used a Transformer XL model. Therefore, it's not clear if SwitchHead is specific to this model or if it can be used with other attention methods. We decided to test rote positional encodings without the XL cache, meaning the attention matrices are square. We tested these models on Wikitext 103 and found that our method also performed well in this case. To understand how the network uses the attention heads, we trained a small, 6-layer, 8-head transformer on list ops. We chose this because small, algorithmic tasks are usually easier to interpret than language models. We also trained a 2-head SwitchHead model with the same number of parameters. Both models achieved around 95% accuracy on a held-out IID validation set, compared to the dense 2-head model, which only reached about 80%. Note that list ops is a classification task and does not use autoregressive masking. We visualized the maximum of attention heads for each layer, for both the standard transformer and SwitchHead. The attention maps were quite similar. However, the initialization and learning dynamics were different for the 2 models, so the overlap wouldn't be perfect even with the same type of model. We also visualized individual attention heads for the SwitchHead model. Often, we could interpret the selection weights. The output experts specialized according to different operations, while the input ones distinguished numbers and closed parentheses. The attention map itself seemed to distribute information about contiguous chunks of numbers. The attention maps of the language models were hard to interpret. However, we visualized the attention maps of the 47M parameter transformer XL and the SwitchHead model and found them to be quite similar. We also identified induction heads in both models. The method most closely related to ours is MOA, which introduces a MO-style attention. It defines each attention head as an expert but shares the key and value projections between them. Unlike in our case, each of the selected experts requires a separate attention matrix, which significantly increases its memory usage. Due to the use of a competitive softmax-based activation function in the selection network, it requires complex regularization to prevent expert collapse. In the original formulation, the number of active heads is high. We also confirmed in our experiments that MOA needs many attention heads to match the performance of the dense baseline, and it is only possible to do so with a significantly higher resource budget than our method. Other researchers have analyzed the attention matrices and concluded that they are usually low rank. Motivated by this, they construct a few global attention matrices, and they compute each local matrix for specific heads by a weighted average of those. However, they average the logits, not the final matrix, so each individual head-specific matrix has to be computed. This means that in the best case, they can only save half of the computation associated with the attention matrix. For the same reason, memory savings are also low. Another proposal is to reweight the contribution of each head by a gating function. However, they only reduce the number of total attention heads by 1, presumably to compensate for the parameters used by the selection logic. Their goal was not to reduce resource usage but to have better predictive performance, which they achieve. They use a softmax-based competitive selection mechanism. To avoid collapse, the gating function is trained only in some steps. The non-competitive sigma-mo method that we also use for our attention mechanism was introduced to speed up the MLPs and not the attention. More broadly, sparsely gated mixture of experts in LSTM networks and mixture of experts in transformers have been introduced. Other researchers have trained a Mo-based LLM and analyzed the scaling laws of Mo models. An alternative method for preventing collapse has been introduced. A hardware-aware CUDA implementation of the entire attention layer, which avoids storing the attention matrix, has been provided. By saving memory bandwidth in this way, they achieve a significant wall clock time speedup, despite that the attention matrix should be recomputed in the backward pass. This is orthogonal to our method and they can be combined for further acceleration.